3.3 is where we leave the descriptive world behind. So we're now getting into why this section is sometimes done at the very end of an intro stats course, because we're going to start making some inference, making some conclusions about a general population or some data points we don't have based on what data we have in our sample. So we're going to move into linear regression. So we're going to fit a linear equation to our data. In order to be able to do that, we need to have quantitative data, right? Numeric data. Only makes sense to fit a line if our actual relationship is linear. And as we sort of saw in that previous example, if you work through it with me, outliers can cause some big issues with linear regression. So we should be using this very cautiously if they're around. And then on the last piece here, it only makes sense the observations are independent of one another. This is getting a little more advanced. But the idea here is if there's any sort of reason that there might be some relationship between the observations themselves, not within the observations, but between them, then we're going to get in some trouble. So a really good example of this is actually our activity from Thursday. In that activity, you worked with a group to get 4 different observations, right? So you had person 1, 2, 3, and 4, and then you had to go find data from another group to fill in your table, right? And the instructions for that exercise were, up to a little bit of interpretation. Where did you start and stop your tibia measurements? How accurate was the other group in terms of finding the person's height? What method did they use? Did they write a line on the board? Did they try to just hold the tape measure where the other one ended, right? So there's actually some dependence among the people who are in your group with the people who are in the other group, based on what they might have interpreted the measurements to be, where they should start and stop the measurements. So you may have ended up getting data from a group and finding them kind of consistently lower than yours or something. That's an issue. So that would be an issue of them not being independent. Okay, there's some sort of grouping that we can go with. Once we fit our line to our data, it's called this least squares regression line, or line of best fit is another way to talk about. It is usually given in slope-intercept format. Statisticians are kind of jerks, though. We don't like the y is equal to mx plus b. We usually write this as y is equal to b naught plus b1x, where we have our intercept and then our intercept and then our slope. And this is because we only talk about simple linear regression here, but there were some good points brought up in the classes on Thursday. What if we wanted to look at other pieces? What if there's other things that might influence your height? We might have multiple things here on the end, lots of different explanatory variables instead of just this one. So that's why we write it in that direction, us statisticians. This minimizes the sum of square residuals, which we're going to learn what that means in a second. But the most important thing here is what we can do with this. We can predict a response for a particular level of our explanatory, and we can look at our general relationship. And so that's exactly what we're going to see as we move forward. So if we want to predict a response, all we need to do is plug in a value for the x, figure out what the line would say our y should be, and voila, we have predicted what we think that outcome will be. We also have this idea of a residual. A residual gets denoted with E, so these things are E. Our predicted values, by the way, we are actually going to use y hat, because they're not the real y, so we throw a hat on it to say this isn't the true y. It's one we came up with. And the residuals are our error. They're how far off we were in our prediction. So we actually did both these things in the activity. There is a formula for this. This is 100% something that should go on your note card so you know how to calculate your residual. So let's go ahead, use these 2 formulas on the next example, and then we'll see about that slope piece. So here we have a scatter plot of systolic blood pressure and weight. And we can already see, right, there's a nice positive linear relationship, very strong. As someone's height goes up, their systolic blood pressure goes up. We've been given a correlation coefficient, our little r, right, showing us, indeed, this is a very strong relationship, very close to 1. And we've been given the actual line of best fit, which is very nice, right? And this is how it'll work on this class. I'm not going to have you use your calculator, type in a bunch of data, and get out that line of best fit. We can do that. You proved it to me on that activity. From now on the test, I will give you the line of best fit and then figure out if you guys know what it is you can do with it. So, first question here says, suppose we know that one person in the sample weighs 188 pounds and has a systolic blood pressure of 136. Predict the systolic blood pressure for a person weighing 188 pounds using your regression model. Well, first thing we need to do is translate these two given values, these two numbers, into actual pieces. Now, when we're into variables, right? When we're doing questions about regression, there's basically 6 things we could possibly be given or looking for. I'm just going to break them down for you up at the top of this. So the 6 things that you might have, we have our actual x, which is just our observed, I don't know why I dotted my v, observed explanatory variable. So this is somebody's actual outcome, our actual value. Our y is our observed response variable. Normally these things are calculated. We have our y hat, which is the predicted response. We have our e, which is our residual. We have our r, which is our correlation coefficient. And eventually we'll have one more thing, which is an r squared, and we'll get to that in a bit. But for now, this is pretty much it. So we can see here, we're looking to make a prediction. So we are looking for a y hat. We need to decide which of these things is our x and which is our y. Lots of ways to do this. So that's why I left this space blank and used that x, the top. This is the most important thing when we're interpreting slope, when we're doing our predictions. The first step, the first step we need to do is figure out which variable is x, which variable is y. In this particular example, this is pretty easy because we can see here we actually have a scatter plot and we know which is the x-axis, which is the y-axis. Life is not always this easy. In fact, on the test, I usually don't have enough space to do a scatter plot, so I don't put them in. So how else are we supposed to do that? How are we supposed to know? Another way is that we predict y. So you can see here the fact that we're predicting systolic blood pressure tells me systolic blood pressure is y. This is somebody's actual, this is one person's actual observation for systolic blood pressure. This is a y, which means this is our x. There are 2 other ways. I'll just break them down now while we're here and we have this space. One is instead of giving you your regression output like this, I could give you the regression output this way instead. I could have done systolic blood pressure is equal to 1.1 plus 0.74 times the weight. So I could have made it obvious that this is y is equal to our mx plus b. So y is our outcome, x is the thing we plug in. And then the last way, the worst thing is if I don't give you anything else, you have to think which is more likely. Just like our cricket chirps temperature example, which makes more sense? Does it make more sense that weight influences your systolic blood pressure or that systolic blood pressure influences your weight? And if I make you use this method, it will be very obvious. So now that we got that, predicting is all about just using our lines. So this is 1.1 plus 0.764 times the x. We do not need this y, it is just extra information. And in fact, something I do a lot on the tests is to give you a little bit more than you need. So you have to figure out what is extra. So we have this is 144.732. We should put units on this. This is a poorly labeled graph, so I'm going to tell you that blood pressure is measured in millimeters mercury, so we're going to do mmHg. And then we find our residual. So residual, remember, this is asking us for a little e, and that formula that you should have on your note card from the previous page, y minus y hat, our truth minus our prediction. So the true value, well, now we're going to use that 136, was 136. We thought the value based on our regression line would be 173.2. So how far off were we? Appears that we are off negative 8.732. And again, residual still has the same units because it's how far off we were, millimeters mercury. And we can see actually all of this on the regression line as well in the scatter plot, which is why the scatter plot's here. So this person, this 188-pound person with a blood pressure of 136, that's this person right there. And when we came up with our prediction, this 144.732, what we did is we came to 188 and figured out that this was what we expected the person to have. That's our y hat versus our y, right? And we can even see our residual, this amount. We were off from this point to this point. That distance, that's our little e, our error, how far off we were. So all of these things are visible on our plot. And now that we've done that, we can actually talk about what that meaning was when it said this regression line is calculated by minimizing the sum of squared residuals. They're taking, when they calculate this, what's happening is that every single one of these distances is being calculated, and we're figuring out which line is going to minimize all of those distances. And in fact, that formula, how to do that, is given below. So again, we see our slope-intercept form, the way statisticians write it. B1, since it's connected to our x, is our slope, and B0, which is floating by itself, is our y-intercept. Terrible handwriting, but you got it. The actual calculations of those things that minimize those sum of squared residuals are given here. To find the slope, you do your correlation coefficient times the standard deviation of your y's divided by the standard deviation of your x's. And to find the y-intercept, you take the mean of your y's minus the slope times the mean of your x's. So this calculation you will never need to calculate. This is more if you get into like a more mathy stats course where they require you to do all these things by hand or in steps, and we don't need to do that. All right, so we need to be able to, though, interpret this interpretation. Again, this is more note card stuff, more things that you're going to be expected to be able to write out about these regression lines. So one thing we want to interpret is the slope, and we're going to do that for our previous example. So I'm just going to rewrite what that equation was. Remember, it was systolic blood pressure is equal to 1.1 plus 0.74764 times our weight, which may or may not be wrong. I'm doing it from memory, but I think that's good. So if we wanted to interpret the slope for this, it says for each one, and then we need to put in our units of x, right? And so we look at our x variable. We said that was weight. What is weight being measured in? Oh, okay, up above, it's pounds. For every 1 pound, go back to stuff we don't need to memorize, increase in, and then when it says x here, it's not asking us for that x value, that 188. It's asking us for the x variable. So that's what it should say. There's actually our x variable, which is weight. So for every 1 pound increase in weight, our y, which is systolic blood pressure, does our systolic blood pressure increase or decrease? That's just about looking at the actual slope. It is positive, so we're going to say increases by, and then we just bring our slope down, 0.764, and then their units of our y, which is still millimeters mercury. All right, so that's what our interpretation looks like. And this, all it's doing is getting back at the basic algebra stuff that you should know, right? We know that our slope is equal to our change in y over change in x. And in stats, very different than what we're used to in a regular algebra class, we don't have a denominator, right? It's not a fraction. We like decimals. So we can just put this over 1. So if we were actually going to graph this, we would say, okay, we're going to go over 1 in terms of x, and then we're going to go up 0.764. And then we'll go over 1, up 0.7, right? So that's all we're writing. We're writing that in words. For every 1 time we're going over on our weight, our blood pressure, our y, is going to go up by that. We're just putting that in words. And so this 1 is always going to go with your change in x. So for every 1 pound increase in x. You could also, I guess, if you wanted to change your scale here, you could write for every 10 pound increase in weight, systolic blood pressure increases by 7.6 millimeters mercury, if you wanted to, if it made more sense for whatever we were talking about. Now, the intercept is also here in terms of interpretation. So let's go ahead and look at that. So our y-intercept, if we were going to graph this line, we would start right at 1.1, and then we would start doing the over 1 up 0.74, over 1 up 0.74 to find our line, right? So the y-intercept is where we cross the y-axis, it's actually the value if our x is 0, right? So we're going to go ahead and write this sentence. For a, and our x is weight still, for a weight of 0 pounds, we would predict, and our y variable here is systolic blood pressure, to be 1.1, because that's our intercept, right? Millimeters mercury. Now, does that make any sense? No. And that's actually something that's fairly common with our y-intercept. In a lot of cases, it doesn't make sense to look at that. If we're talking about height, there's no such thing as a person who is 0 feet tall, right? If we're talking about arm length, there's no such thing as a person who has a tibia that is 0, right? So these things are not useful for us. That one is not necessarily used for us. The slope will always have an interpretation. Y-intercept can be useful if we were talking about like hours spent studying. There will be people who put 0. Hours working, there will be people who have 0. So it does occasionally have some use. So I'll stop this video and start again with the examples on the next page.